Okay, we're going to talk about optimization. So in your homework, you had to do a problem where you were given 800 meters of a wire fence or electrical fence, and you have to make a rectangular lot, and the river is going to flow by one side of this rectangular lot that you want to mark out. So the first thing I'm going to do is draw a happy little tree as if I'm Bob Ross. And we would like to incorporate the tree because it provides shade for all the little animals. So the next thing I want to do is draw a rectangular plot. But now I need to only do 3 of the 4 sides of the rectangle because the river, we don't want to keep that restricted. We want the animals to go and drink the water when they're thirsty. Because even though there's a tree there that provides shade for them, they still need water to survive. So anyways, what we need to do is find the maximum area that we could cover with 800 meters of electrical fence wiring. So because it's a rectangle, we know that the width is going to be the same, but we don't know what it is, so we're going to label that as x and x. The problem is determining what the length of the rectangle will be. So somehow we need to make the length dependent upon x. In other words, we have to mathematically let L be some sort of variation of x, or write it as a function of x would be a better way to say that. And so we don't have a lot of information other than the fact that the total length of wire that we have to use is 800 meters. So what we would like to do is we're going to say that 800 meters has to equal, well, 2 times x. Oh, I got to fix my screen here real quick. I didn't like the way it was writing. So 800 meters equals 2 times x plus L. So now if I take this equation and solve for L, what I need to do is if I subtract 2x from both sides, I now can list L as a function of x. In other words, L will equal 800 minus 2. So now I have both my width and length in terms of x. So if I wanted to write a function of area, remember that area is equal to L times W, and we just said that L was equal to 800 minus 2x. So my function of x for area is 800 minus 2x times the width, which is x. Now our goal was to find the maximum value, or the maximum area based on this equation. So when I expand my equation or function of x for area, I get 800x minus 2x squared. Now to find the maximum value, what I need to do is take the derivative of this function, set it equal to 0, and then that will give me the maximum value. So what we need to do is take a of x, which is equal to 800x minus 2x squared, take the derivative of that. So a prime then would be 800 minus 4x using the power rule. If I set that equal to 0, I get 0 equals 800 minus 4x, or x equals 200. Now what this means is that our area is a function of x, and so if we were to graph that function, we would see that the y value is a of x. And if we were to graph that when x equals 200, because our function for area is a quadratic with a negative leading coefficient, we're going to get a graph that's parabolic in shape where the vertex occurs at x equals 200. Now what we've done mathematically is we found where the tangent has a slope of 0. That occurs at the maximum of this particular function. So that's the maximum value for x. Well, to find the dimensions of this, what we would need to do is let x equal 200 and plug it back into our picture. So the width is actually x. So what I would do is I would let x equal 200, and so that means that both widths would equal 200, and then plug that into the function for the length and find out what the length is. So we just need to verify that data, and it's all based on the derivative of the function of x for the area that we kind of constructed here. So let's do that. Oh, and one last thing, when I'm done finding the dimensions of this, it should add up to 800. So let's try that. So x equals 200. x equals 200. And then I have 800 minus 2 times 200, which is 800 minus 400, which is 400. If you add them all up, they equal 800. So that would be my maximum value for x. Now on our next problem, we have a similar optimization type problem. But what we need to do is, it's really kind of simple. We just need to construct a container. Let me draw a picture here. So in all these problems, what we're going to do is we're going to write a function, take the derivative, and find the minimum or maximum value, which occurs when the derivative is set equal to 0. So we have a square-based container, all right, and we're asked to, we're going to run through an optimization problem with this. So the information given to us is that it has to have a square base and the volume has to equal 500 feet. The engineer is charged with the task of taking sheets of sheet metal and welding them together, and so they want the minimum amount of sheet metal used to construct a container with an open top that will hold 500 cubic feet. So the first thing I do is write down the general form for volume, which is L times W times height. Well, as you can see, L and W will be x because the area or the base is x squared. So I just need to write h as a function of x. So one way to do that is to plug in x for L and plug in x for W, and then given the fact that the volume has to equal 500, I get 500 is equal to x squared times h. Now if I solve this algebraically for h, I can rewrite h as a function of x. Simply what I need to do is divide both sides by x squared, and that yields 500 over x squared equals h. So I'm going to consider h 500 over x squared. Now I have all of my dimensions in terms of x, so I can write an equation of x for a certain thing. Now I don't want to do area of the base, and I don't want to find the volume. If I was an engineer and I needed to figure out the minimal amount of sheet metal needed, what I'm really talking about is the surface area of the box. So I need to find the smallest surface area of this box so that it'll contain a 500 cubic feet of whatever it's going to contain, probably some sort of liquid. So essentially I need to write an equation for the surface area. There are different equations that are pre-formulated that you could write out, but we could also just kind of go through step by step and write down what we need to write down. So the surface area is the important thing that we need, and we need to write it in terms of x. Since we want to use the minimum amount of surface area, once we write this equation and take the derivative, there should be some sort of negative leading coefficient of some sort because we want a minimum value. So we're gonna be looking for a parabola type function that opens up, and we're gonna look for that little valley in the hill. So to construct this equation of surface area, what we really need to do is add up all of the sides of the box and calculate the area for each side. So I see that I have 4 sides that are the same area, which is h times x, and then I also have the base, which is x squared. So first let's write it in general terms. So I'd have 4 times h times x, alright, and I'm going to scribble these in, it's kind of hard to see. So I'm going to have 4 times h times x, which is 500 squared times x. You know what, let's just write that as h times x so you can see the connection. So it's h times x plus x squared, which is the base. Now if we had a lid on that, we'd say 2 times x squared. Now I'm going to plug in what h is. H is 500 over x squared, x is just x, and so now I have a quadratic type equation that I need to find the minimum value for. Now the leading coefficient is actually a positive 1, which is a quadratic that opens up. So that's good, no mistakes yet. So now I've got 2,000 over x plus x squared. So I want to set this equal to 0 and find the solution or find the zeros of this function. But first I need to take the derivative of this function. So the surface area can be calculated by 2,000 over x plus x squared. Now to find the minimum value, I need to take the derivative, which really gives me the slope of the tangent line. By using the power rule, the derivative is negative 2,000 times x raised to the negative 2 plus 2x. Again, I'm going to need to set this thing equal to 0. I'm going to toss that x to the negative 2 down on the bottom, so it's all over x to the positive 2. And then I'm going to have to set this equation equal to 0 and solve. By doing that, that will give me the value for x where the slope of the tangent line is equal to 0, which is where the vertex is of our quadratic equation. So what I want to do then is set that equal to 0 and solve. I think one thing to take under consideration or to think about is the fact that I need to get rid of this x squared thing. So one way to get rid of the denominator is to multiply the whole thing by x squared. So if I set it equal to 0, I don't like that denominator of x squared. I can take the whole equation and multiply it by x squared, and that'll cancel the denominator. So let's do that. Let's take our whole equation and multiply it by x squared, and then we distribute the x squared through, and we'll get it'll be a little bit easier for us to solve. So I mean, there's other ways you can solve it, but at some point we're going to have to do that. So when I push that x squared through, I still get 0 equals negative 2,000 plus 2 times x cubed. Slide the 2,000 over to the other side, divide by 2, and I end up with 1,000 is equal to x cubed. When I get 1,000 is equal to x cubed, it's pretty easy. And I'll write out each step so you guys know what I'm talking about. So I have 1,000 equals x cubed. Now I just take the cube root of both sides. In other words, I'm looking for a number that when I raise it to the third power, I'm going to get 1,000. So 10 times 10 is 100, times 10 again is 1,000. So the cube root of 1,000 is 10, or x equals 10. Now we're almost done, but not quite. That just means that x equals 10, so we're going to have to plug this back in. So the base is 10 by 10, and the height would be 500 over 10 squared, which is 500 over 100, which gives me 5. So the dimensions of this box is 10 by 10 by 5. Plug that back in. 10 times 10 times 5 does in fact equal 500. And that's how you find the minimum surface area of a box that has a volume of 500 cubic feet.